Welcome everybody. So now it's going to be a pleasure to introduce Mathias Beiglböck, who is going to talk about all adapted topologies are equal.
Hi, thanks a lot for this opportunity. Thanks for the introduction. Thanks a lot, Live. I will speak about results which are joined with these people. This will be more of a survey talk, so there will be many results which are not by us, but which are by other people. So since this is a survey talk, this could give the impression that this is somehow an area which we invented, and I want to very much emphasize that this is not true. So this is a very old area which has many different roots. We specifically got interested because of applications in mathematical finance. You shouldn't be scared. There will be almost no math finance in this talk. I just want to very briefly sketch what the original problem was. I mean, so in math finance, what you usually do is you pick a model and you hope that this is close to reality, to some real evolution of some asset price process. And then if this is close to reality, you hope that your predictions about prices or trading strategies are close to useful in reality. And of course, I mean, we would like to have statements like this in our field. And a big problem with this turns out to be that something like this is not at all true. And the reason is that, or it's not at all true, in particular, if you look at usual topologies. So for simplicity, assume that we are in a discrete time framework. Then in probability, we would like to look at some version of weak convergence, and then you find out that any type of this statement is not true. And the very simple reason is that being close in something like Wasserstein distance or weak topology doesn't tell you much about the probabilistic properties, like being a Martingale or being almost a Martingale. And this completely screws up things if you want to prove results like this in finance. So our main motivation was try to understand what kind of closeness one should use at this stage. And I should say that this is not my work. This goes back rather to work of Beatrice Achayo and Julio Bakov, and is in some sense also present in an earlier work of Jan Dolinsky. Okay, so to be more concrete, during this talk, we will mainly focus on finite discrete time. I'm talking here about Rn. So the idea is that we have a one-dimensional state space. Instead of R, it could be an arbitrary Polish space, but it won't matter during this talk. And then we ask questions like, when are stochastic processes similar? And what we mean by this is, when are they similar in the sense that their laws are similar to each other? And I want to illustrate what we are after with a simple example. In any case, I think this example is the most important message of my talk. So if you have questions concerning this example, please go ahead and ask. So the idea is I want to consider a simple process which has just 2 time steps. And the evolution of this is described through a probability measure P. And this probability measure is just saying start at time 1. And then with probability 1/2, you go up, or with probability 1/2, you go down. So super simple one-step Martingale. And I want to compare this with another process, which depending on perspective is similar or not similar. So I want to compare this with a process which looks like this. So let's zoom in a little bit to understand what's happening here. I want that at time 1, the starting points of this process are an epsilon apart. So this is my process yt, and its law is maybe described by a probability measure p epsilon. And now we want to consider 2 exercises. And the first exercise is, this first exercise we want to kind of show that these 2 processes are close. And to do that, we calculate the Wasserstein distance of these processes. So we calculate one Wasserstein distance, which for the purpose of this talk is simply given as an infimum over mappings from R2 to R2, which have the property that they push the one law to the other law. And whenever we transport a particle with this mapping, we pay a cost, which is just the distance. And then in the end, we sum over all particles. Okay, so the first exercise is understand what this Wasserstein distance is. And maybe you can use the chat if you have an answer to this. And yeah, I mean, I don't know. I have co-authors present, so at least they should know the answer, yeah? A second exercise, this is looking at something different. This is trying, so I mean, probabilistically, we think that those processes are not so close to each other. I mean, one process is a martingale, the other one is deterministic. And with the second exercise, we would like to understand how this leads to some non-similarity in probabilistic terms. So my second exercise would be look at optimal stopping problems. So you take an infimum over expectation of x tau, where tau is a stopping time. And well, first you want to calculate it for the left-hand side process, and then you want to do the same problem for the right-hand side process. Okay, so this, I mean, either this version with the chat doesn't work for me, or the exercise is too hard. But so far, I don't see answers to the first question. I mean, I'll give you a hint. So what your good mapping is doing, it is taking this kind of path and it is attaching it to this kind of path. So this is one half of my mapping T, and the other half of my mapping T is doing the same with the other path. And in each case, the distance of the origin and the target is going to be less than epsilon. So maybe we can agree that this is at least smaller or equal than epsilon, yeah? So this is what this first part is trying to communicate, is that in Wasserstein distance or in any other version of some weak topology, of course, those 2 processes are very close to each other. The second exercise, well, the first process is a martingale. If you stop a martingale, then you just obtain the value at the beginning. So here we have the value 1. And on the other hand, in the second process, we could be a little bit smarter. So we could stop the second process. If we are in the upper path, we know that in the future, we're just going to go up. And so it's a good idea to stop the path here. Whereas the other path, here we know that we are going to be smaller in the beginning. So here we go on. And in the end, what we get here is roughly 1/2. Okay, so the story I'm trying to tell here is if you are close with respect to weak topology, this will not at all tell you something about being similar in probabilistic terms. And in particular, if you look at probabilistic decision problems, then you obtain very different results potentially. The goal of this talk is to discuss what is a good notion of topology, or what is a good notion of distance that allows you to separate such different probabilistic behavior. And I mean, you might expect that we are not the first ones to ask such questions. So what I will do for the next portion of my talk is I will discuss approaches which people in history have come up with to try to deal with similar questions. And the first such topology is so-called extended weak topology of David Elders. I mean, David Elders is starting to associate to the law of the process the so-called prediction process. And down here we have the definition of the prediction process. But actually, I think this definition is relatively complicated. So unless you're very sharp and fast and I'm talking too slow for you, then I suggest you just don't read this definition if you don't already know it, because, or at least it took me quite a while to digest what this is really supposed to mean. And we'll also not need it much in the rest of the talk. The reason or what we need about this prediction process is that this prediction process is a way to embed this space of laws of processes into a bigger set where the corresponding objects have much finer structure. So where you have, because you're living in a much finer environment, you can say some, oh, I'm super happy that I have some question here. Is there a typo in phi? Can you be more specific with this question? The image of phi. Okay, now I get it. So the question is if this is the typo, maybe? I think, so it's not a typo, it's, so here we have the whole of Rn, and here we also have the whole of Rn. But of course, you are right, it would not be necessary to include this. You would have, in fact, the same information if you forget about this first coordinate, and also if you forget about the first coordinate here. It's not super important for this talk. What is important here is what we have here. These are all much larger spaces. We can endow each of these spaces with a weak topology. Then we have a product of many different spaces, which are all Polish spaces. So in the end, we get a Polish space, and then we look at probability spaces up there. And then we have some very complicated object, but because everything is still Polish, we still have a usual weak topology in this very big space. And then the idea is we can pull this very big topology back to the original space. And then this gives you on the original space a topology which is for n bigger or equal than 2, strictly finer than the usual weak topology. Okay, now this is really a typo, yeah. Thanks a lot, Stan and Julio. So this should be x1, x2. Okay, and one comment here, this topology of Elders, this is, for instance, fixing the problem which we had in the previous slide. So with respect to this extended weak topology, optimal stopping will be continuous. And another such topology was introduced by Martin Hellwig. He's an economist. He's interested in stochastic games. And what he's doing is he's always separating the process into two components, into past and future. He defines some kind of disintegration of the future with respect to the past, which is similar to what Elders is doing. And again, this gives you embeddings into spaces which are more complicated, but still carry a weak topology. And then you pull back your weak topology there and obtain a finer topology on the original space. And in the case of Hellwig, he obtains what he's calling the information topology. In the next step, I want to discuss a topology which is more closely related to the Wasserstein topology we have seen in the beginning. So here I have put again just the usual definition of Wasserstein distance as we had it on the second slide. I mean, it's not really a definition because we are only considering mappings, but if the measure P is somewhat continuous, that's no issue. And I want to rewrite this push forward condition a bit. I want to make explicit that this mapping T is a mapping from Rn to Rn, and hence it really consists of n individual mappings. And I mean, if I write it like this, then you already may recognize the similarity to a stochastic process. And now if you think probabilistically, what this mapping T is doing, it's taking the first T coordinates of the measure P and takes them to the first T coordinates of the measure Q. And if you want to do this in a way that respects the flow of information, then probably you should do what you usually do in probability. You should ask that this mapping, that this family of mappings as a process is adapted. And this is precisely what's happening in the definition of causal Wasserstein distance. So the idea here would be to put this condition of adaptedness into the condition of matching probability measures. And if we just do it like this, then we obtain something which is not symmetric, and therefore it will not yet define as symmetric. But of course, you can easily make it symmetric by just switching the order of Q and P, and then taking something like the maximum or the sum of those two components. And what we obtain in this way, this we will call a symmetrized causal Wasserstein distance. Okay, and then, I mean, if you know optimal transport, then you're of course aware that usually we do not look just at mappings T, but rather we look at couplings. So also here, if we want to make the official definition, then we would refer to the set of couplings, and which are in addition causal. And once again, I want to say that this is confusing, and I recommend that you don't read it. I mean, the idea is a mapping is adapted if the first T coordinates of the mapping depend only on the first T coordinates in the origin. And this is somehow rephrased here, that saying that if you're given x1 to xt, then y1 to yt is independent of the tail. Yeah, so I think if you think hard and concentrated, then this is the very natural. This is the natural definition, but I don't know. It takes some digestion to find it that natural. Yeah. Okay, I want to come to another construction, and in a way, this is very similar to this causal distance. This is a construction which, I mean, early work in this direction is going back to Rüschendorf. Independently of Rüschendorf, this was discovered by Pflug and Pichler, and Pflug and Pichler, they come from optimization and statistics, and I mean, they are more interested in the applied side, and I mean, they have many interesting papers about applications of what they call the nested distance. And more recently, in continuous time, coming from a very different direction, this was also investigated by Bion, Nadal, and Talay. And this distance, this is usually called nested distance because if you look at usual definitions of this, then this is defined in some iterative way. I have here put an equivalent definition which makes the connection to causal transport more apparent. So here the idea is you don't symmetrize in the end, but you symmetrize already here on the level of couplings. So already on the level of couplings, you say that pi as well as what you obtain from pi by simply switching the roles of x and y is also something which is causal.
Yeah, I think I have a quick question. When you talk about these Markov constructions, what it comes to my mind is that usually you want to build a upper bound for whatever distance you want to compute, and you do it with a coupling, and usually it's very convenient to think about augmenting your space with some randomness, then defining a clever Markov chain that couples the two things, and that's it. I mean, are these distances related to that concept?
Thank you for this question. Honestly, I'm way too nervous to say anything useful there. No, of course, it's a very good question, and of course, my co-authors in the chat will give the appropriate answer, but I don't have the time to do it here. Okay, so I will continue. Okay. Something with what I want to emphasize is that all these researchers are coming from very different areas, yeah, and actually at very different times, so they are not really aware of each other. And as a consequence, they are not looking at each other's work and not at the connections. Okay, now, the spoiler was in the title. Our main result is that all of these different concepts actually lead to the same topology. Okay, if you know weak topology, then of course there's many definitions of weak topology, and it's really an exercise to understand that they are related. I want to make the point that, at least for me, this was not the case here. Yeah, so I found it very hard to understand the connections between these different definitions. Yeah, and also very often, if you do joint work, then you think maybe I could have done the same alone. It just would have taken longer. Okay, so I want to say this is certainly not true here. So I'm very much relying on the work of my co-authors in this result. Yeah, and somehow what seems to make this hard is, on the one hand, there is some, or hard for me at least, there is some analysis component on the one side. And this has to be intermixed in many clever ways with some algebraic arguments, which help you to step up and down of these different levels of forming another set of probability measures, and so on. And this is what makes this not so clear. Another hint why this is maybe not a trivial equivalence is that in all of this, for all of these topologies, you can actually attach natural metrics to these topologies. And these metrics, they are not equivalent. Yeah, so not even if you restrict to probabilities which are concentrated on some compact domain, they are still, they are not equivalent as metrics. Yeah, in applications, I think knowing that those are equivalent, this is useful because, well, some of these things feel much stronger than others. So for instance, if you know convergence in nested distance, then this is usually a very strong assumption to prove something. On the other hand, it is in itself, I think it's usually very hard to establish. You don't see the result. Okay, the result is in the title. This is kind of saving me. The result is all adaptive topologies are equal. I hope that I can repair my screen. Yeah, I cannot repair my screen. This is the result. Oh, sorry. Okay, so the last 10 minutes I've been talking about the result which was not seen. Thank you for your patience. Okay, our result is all topologies are equal, and the reason it's useful is that yeah, depending on what you do, you want to use very different definitions. If you want to prove something, you want to have the nested distance. If you want to prove that something is true, you want to start with Helvig. If you look for applications in my finance, then usually you would like to look at causal transport. Okay, so these were 4 topologies which have been investigated in the history. In some sense, this result is more universally true. So other topologies which maybe have not been considered so much, well, one is building on this notion of equivalent, or on a notion of equivalence of adapted processes of Hoover and Kiesler. They come from logic. I will not explain what they are doing. But again, it leads to a natural extension of the usual topology. And again, it's the same extension. And 6 is another way to form a topology from a causal Wasserstein distance. And again, it turns out to be the same. And in 7, I mean, if you're working a bit with couplings, then you know the Knote-Rosenblatt coupling, which is a very specific coupling, which is discriminating between coordinates in Rn, and you can take the costs of Knote-Rosenblatt and use it to define a distance. And once again, it turns out to give you the same kind of topology. Yeah, so I think this is a nice fact, and in the sense that if many people independently come up with something which then it turns out to be the same thing, there maybe is something natural here. Next, I want to briefly discuss some consequences of this. And in these consequences, I mention another fact about these weak adapted topologies, which is often playing a very important role. Namely, I mean, if you think about usual weak topology, this is such a useful concept because we understand so very well what relatively compact sets are, thanks to Prochorov's theorem. Something which makes working with these adapted versions very easy, or often very convenient, is that also for this finer, actually much finer topology, you still have the same pre-compact sets. The first application which I want to discuss is going back to this optimal stopping problem which we had in the beginning. So I already mentioned that if you look at the extended weak topology of David Elders, then with respect to this topology, you have continuity of optimal stopping with respect to the underlying measure with which you do the stopping. And it turns out that as soon as you want to have this property, you automatically have to use at least this weak adapted topology. So this is the weakest topology which gives you continuity of optimal stopping. And I mean, once again, this is something, I mean, to prove such a result, it's very important to know the equivalence between these different definitions, because getting continuity from the nested distance is very easy. On the other hand, proving Helvig from convergence of optimal stopping problems is also easy. And the hard thing is to connect those other two. A second application concerns the finance motivation I mentioned in the beginning. I mean, typical things you do in my finance are pricing, hedging, utility maximization. And in all these instances, you can ask yourself, if you slightly change the underlying measure, does it have an effect on the outcome? Or does it only change the outcome very little? With usual topology, everything fails very badly. If you look at some adapted Wasserstein distance, then it turns out that you actually get Lipschitz continuity. And I mean, okay, for my finance applications, of course, you would like to also look at continuous time. So this works also in continuous time. And then in continuous time, you can ask yourself, we are imposing so much abstract structure here. Do we actually still capture something of what is really going on in reality? And I would claim that in fact, this is really capturing the right phenomenon, in the sense that if you go down to very simple probabilistic models and the simplest possible financial derivatives you can look at, then you already see that these Lipschitz constants are sharp up to some numerical constants. So it really seems that this adapted Wasserstein distance is capturing what's going on the level of changes in math finance. Yeah, the third result, where we need this heavily, this is concerning denseness of adapted processes in causal couplings. Yeah, so as pointed out by Dan Lecker, if you a good motivation or for causal transport to be well motivated, what you would actually want to have is really that adapted mappings are dense within the causal couplings. And it turns out you can prove this. And this is an upcoming paper with Dan Lecker, and it's very much again building on this equivalence of topologies. Another problem where this appears to be crucial concerns stability of Martingale optimal transport. So in usual optimal transport, stability is something very basic. In Martingale optimal transport, this has been open for a couple of years, and yeah, it's now proved in these independent papers.
So we have a question on the chat.
We have a question. Thank you.
Yeah, maybe it's interesting.
So I would say this result applies to complete and incomplete markets at the same time. I mean, there is, it's always, incomplete markets, what it would say is that something which is a super hedge in one model is almost a super hedge in all closed models. And this is not related to whether we look at something which is complete or incomplete. Yeah, maybe I don't want to discuss it much more now, because I think I'm a bit behind time, and it leads a little bit away from my talk. Yeah, another application concerns weak optimal transport. So weak optimal transport, this is an extension of classical optimal transport due to Nathalie Goslan and his co-authors, Alibert Bouchit-Champignon, and due to Alphonse Jourdain, rather independently. The idea here is to extend the framework of optimal transport in order to cover a number of other problems which are not precisely fitting into the classical optimal transport. Yeah. So, I mean, the original motivation stems from geometric inequalities, but actually there is, I mean, this is a very incomplete list of topics which fit into this slightly extended framework. And something which was a little bit strange in weak optimal transport, or at least to me, was that proofs of very basic results, which are very simple in optimal transport, like existence and duality, they turned out to be much harder in weak optimal transport. And also, I mean, first results or early results on existence duality, they usually use a lot more conditions in weak optimal transport, and somehow seem to be more complicated than necessary. And it turns out that this magically goes away if you look, if you consider the problem with the help of such weak adapted topologies. Yeah. So if you use this weak adapted topologies, it turns out that you can basically use the very same ideas as in the classical framework and obtain such results in the expected generality. And then, of course, this has a number of applications in fields which are covered by this weak transport framework. Yeah, and then final application that I want to mention, this concerns functional inequalities on Wiener space. So I think that Rémi Lassalle has some proofs of Palagrand's inequality, log Sobolev inequality on the Wiener space through causal transport. And I think what he sees there is, it's really, I don't know, to me, this is really sheer beauty. Yeah, and of course there is many names and papers which are missing here. So yeah, I apologize that this is very incomplete here. Now, in the final part of my talk, I want to, I'll try to take a bit of a step backwards and try to understand what could it be the bigger picture of what we are doing. And I want to do this through an analogy. Yeah, so if you look at probability measures on Rn, then what Wasserstein distance is doing for us, it is imposing a very nice geometric space structure on the space of probability measures. And I mean, of course, this has had tremendous applications of classical optimal transport. And somehow what we do now is we again look at, I mean, so far we've only been looking at canonical processes, and these canonical processes, they are probability measures on Rn again. But we have discussed that for several probabilistic problems, you should look with a different topology and maybe with some adapted version of Wasserstein distance. And of course, the question you could ask now is, can we do something similar? Yeah, so is there, maybe can we define or can we find some nice geometric properties for the set of stochastic processes? And I mean, we are certainly not there yet, but I want to still discuss some properties of this space of canonical processes with respect to Wasserstein distance. And the first thing which one should notice is that adapted Wasserstein distance is not complete on the set of on P of Rn. I mean, P of Rn, it turns out that this is actually a Polish topology, so there is some complete metrics here, but the natural metrics are not complete. And there is a good reason why these natural metrics are not complete, yeah? And to explain this, I want to go back to this example which we had at the very beginning. Yeah, so we were looking at processes which are only a little bit apart from each other in the beginning. So this law I would call Pn. And if you look at this sequence of processes, then it turns out that Pn is actually a Cauchy sequence with respect to adapted Wasserstein distance. And of course, in the limit, what you don't get is that those 2 points just become 1 point, yeah? So this would be the limit in the usual topology, and here we are finer, yeah? So what the limit would be, what we would expect the limit to be, at least informally, this would be something where you simply have this point twice at the very same position, but really 2 times this point. So somehow we would expect that such a sequence converges to this type of limit, and we somehow have to add this this type of limit to our space. And actually, I want to discuss 2 different ways of looking at this completion. The first way, I first want to explain it in this very simple case where n is equal to 2. What you do here is some Vershik type construction. Yeah, so you look at the space of probability measures on R. Here you have a Wasserstein distance with respect to the distance, which is the usual modulus. And then you take a product with R and you obtain a bigger space. And on this bigger space, you have a Wasserstein distance with respect to another metric, which is now the usual modulus with respect to the first 2 coordinates, plus a Wasserstein, an ordinary Wasserstein distance with respect to the second coordinates. Okay, and it turns out that if you do this construction, then the completion of P of R2 with respect to some adapted Wasserstein distance, then this is this space P of R times P of R, and this Virchow type Wasserstein distance on this bigger space. And okay, so this is 2 coordinates. If you have more coordinates, then you'd iterate this construction. And I think this is nice from a geometric perspective or an optimal transport perspective, but it's losing a bit the connection to stochastic processes. And so I want to present a second point of view on this, which is making the connection to stochastic processes better. And the concept which we consider here is so-called filtered processes. So a filtered process for us, this is some probability space with some filtration and then an adapted process. Yeah, so far we've only been considering canonical processes. Here we introduce also a non-trivial filtration. Okay, so as soon as you have arbitrary spaces omega, then of course you introduce a lot of redundancy. Yeah, so I mean, you can have very different omegas, but still you have essentially the same space. So you somehow want to factor out something. And what Hoover and Kiesler are doing is they say, let's identify 2 such filtered spaces if everything which a probabilist usually is doing is the same. Yeah, so they are logicians, they understand model theory very well, and they can make precise sense out of this. Yeah, saying that we say that 2 processes are the same if everything you can do in probability for these 2 processes is going to be the same. Now, a first result which we have is saying being the same probabilistically is actually the same as having this adapted Wasserstein distance equal to 0. Yeah, so here we look at an extension of the adapted Wasserstein distance we had before, but you just put filtrations where in the definition of couplings, and then you find your definition of this adapted Wasserstein distance. And yeah, this is just a more probabilistic instead of logician way of expressing that those 2 things have the same properties. And now the second theorem says that the completion of the set of canonical processes is exactly the set of all processes together with some filtration. Yeah, so I mean, in probability, we are all the time considering stochastic processes with filtration. Here, it turns out that this appears naturally as a completion with respect to this adapted Wasserstein distances. And specifically, what this gives you is an identification of such processes with filtration to this Virchow type construction. Okay, that's it. Thank you very much for the attention.
Very good. So now we would like to see if we have some questions from the audience. So you can either type your questions or there is a button to
thanks, Nathanael.
So let's see. Okay. No questions, maybe.
Honestly, I want to take advantage of having a bigger audience than usual, and I would like to put an open question here.
Okay.
So as long as there is
no
other question.
My question, because Andreas promised me that I could ask all questions I wanted if I agreed to share the session. So go ahead with your open question, and then I
mean, my question is, suppose processes X, Y with filtration have distance 0. Then we know all probabilistic properties of these 2 processes are the same. So specifically, we know that if we look at, if we have any process G and we look at the stopping problem for the process X, then the result is the same as what we look at if we look at the stopping problem for the process Y. Yeah, and I mean there is other ways of identifying stochastic processes like LDOS, and for this is not true. But if you do this with a nested distance or adapted Wasserstein distance, then you obtain that this is true. What seems plausible, but what we are not able to show is what about the converse? Suppose that two stochastic processes are the same in terms of optimal stopping. Yeah, so I mean, this is for me from one way of formalizing that they are the same in terms of sequential decision problems. Does this already imply that these two processes are completely the same? And I mean, of course, there is like a million open questions in this area. And I mean, we're working on some of them. And I think on this one, we would like to give up.
So let me see. I think you answered most of my questions, but there is one that I wanted to ask. This Wasserstein nested, presumably comes with a variational principle, no? That you can write if you are patient enough, you can write this this W nested as some infimum over Lipschitz functions.
Yes, I mean that's some supremum or Lipschitz functions maybe.
Yeah, maybe. Yeah.
Yeah. That's true, but I mean, it's going to be Lipschitz functions on probability spaces of probability spaces of probability spaces.
Okay, so there is no other simpler variational principle for some of the topologies that you mentioned that one can use instead of that.
Okay, I mean, what you mentioned, I mean, I think it's a super good question. That what is there some Kantorowicz-Rubinstein theorem for this adapted distances? Yeah.
Yeah.
And I mean, honestly, this is somehow also what was driving my question here. That if you take I mean, on the right hand side, I mean, restrict to even maybe Lipschitz G, and take a supremum over all stopping times, is this going to give you a distance which is, it's not going to be exactly the nested distance, but maybe it's something very similar. Yeah.
Yeah.
So actually, I mean, yeah, your question is somehow what's behind what I wrote here. Yeah.
Okay. Okay, so let me check. No other questions on the chat. So Andreas was proposing something that I don't know how to do, which was unmute everybody at the same time.
Yeah, you want me to count you all in and I'll unmute you?
Okay, yeah, I found the button. So I'm going to unmute everyone so we can clap your hands together and thank you one more time. Let me see if this is going to work.
Yeah,